Have you ever wondered how some people are capable of representing the graph of any function just by having a look on its formula? Well, in today's episode, we uncover that by using the specific case of quadratic function. And by the end of this video, you will be able to understand how a quadratic function can be represented just by using three really interesting indicators: the roots or the x-intercepts, the vertex, and the axis of symmetry. So without losing any time, let's jump right in. In order for us to represent the curve of this function, we can plug a specific value to x and find out what is the corresponding y value. Well, it works, but a most powerful way is to go through a really key and interesting process, which is, you may have guessed, completing the square. So if you don't know what is completing the square, I do highly recommend you to check my last video. I'll plug the link in the description. Let's complete the square here. To do that, we first need to divide our equation by the coefficient of x squared. X over 2 equals to x squared plus x minus 12 over 2, which is 6. So the next step will be to divide the coefficient of x by 2, and then I have directly the form x plus 1 over 2 square minus 1 over 2 square minus 6, x plus 1 over 2 square minus 25 over 4, and then the final expression of our completed square would be x plus 1/2 square minus the square root of 25 is 5 and the square root of 4 is 2 square to keep it equal. That is the final expression of a completed square, and this is fx over 2. We've completed the square, and from this form we can extract all the information we need for the graphical representation of our function. For that purpose, we first need to know what are the roots. We have x, 1, 2, that would be the different value of x, equals to minus 1 over 2 plus minus 5 over 2, which is equal to, in the first case we will have minus 1 plus 5 over 2, and in the second case minus 1 minus 5 over 2. That here equals to 2 minus 3. So these are the roots, or the x-intercept, the point where the curve hits the x-axis. And then we have the axis of symmetry. In fact, the axis of symmetry is a straight line that's divided the parabola into two identical mirror image halves. And it has the equation x equals to minus 1 over 2. That is in fact the negative of what stays with x in the square. Next comes the vertex. The vertex is the lowest or the highest point of the curve. That's in fact where the parabola changes its direction. You will have the coordinate, let us call it a. You will have the coordinate ax and ay. The axis of symmetry passes through the vertex. That means ax has exactly the same coordinate, minus 1 over 2, and then ay, which is the y coordinate of the vertex, will be this number multiplied by the coefficient of x squared. Really important. In our case, we have minus 25 over 2, which is minus 12.5. Additionally to all that, we can plug 0 into the function and try to find out which value f we have. We have minus 12. Minus 12. So we have a lot of information here, and we can now plug our function. First, what we need to do is we can represent the roots that are 2 and minus 3. I have 2 here, the first point, and minus 3. Really good. And then the axis of symmetry, x equals to minus 1 over 2. Minus 1 over 2. Axis of symmetry done. Now the vertex, it has the coordinate ax and ay. Ax is minus 1 over 2, this is this here, and ay minus 12.5. 12.5 is somewhere here, and I got a point A, that is the vertex. F from 0 equals to minus 12, which is here. We can now represent our parabola. Since we have all these points and the axis of symmetry, I think it is obvious that the parabola opens upward. But if you don't have this, how can we know that? You just have to have a look at the sign of the coefficient of x squared. And when it's positive, it tells us that the parabola opens upwards. When it's negative, this opens downward. Really important. Now we can represent the parabola. To have it a little bit more precise, we can just look at the value of f when x had specific value. When we plug 1, we become 4 plus 4 minus 12, and this is minus 8. 1 minus 8 is here. So this is a point where the function passes through. Where we have something like this. This is how the graph of our function looks like. It may not be sharp or precise enough, but I hope you can understand the main process behind this. So we have the axis of symmetry, which is that line that cuts the parabola into two parts that looks pretty the same. And then we have the vertex, which is in our case the lowest point of the parabola when it opens upward. And then we have the two roots that are the point where the curve hits the x-axis. I also want to introduce to you another method that can help you having a kind of mind representation of how a quadratic function could look like. And this is not as precise as this one, but it can help you just representing the function and having a quick idea of how it looks like. The core idea of that other method is to assume we have another function. Let us call it g. Gx equals to 2 times x squared. And when here I multiplicate all the equation by 2 to have 1 here on the denominator, I have 2 times all this. 2 times x plus 1 half squared minus 25 over 4. And if I try to replace the argument of g by x plus 1 half, I will become g of x plus 1 half is 2 times x plus 1 half square. I just replace x by x plus 1 half. And then I decided to add this other coefficient multiplied by 2 behind. I will have here 2 x plus 1 half square minus 25 over 2. That will be fx. And as you can see, fx can be represented or can be fabricated from g just by changing the argument and by adding another term here. We say to represent the curve of fx, we need to take the one of gx and making a kind of translation by a specific vector. That means the curve of x is the translation of the one from g by the vector v that has the coordinate minus 1 over 2 and exactly the other one, and 25 over 2, which is 12.5. If you look exactly, you can see that it corresponds to the vertex that we have by the other method. The graph of g, which is 2 times x squared, is something that looks pretty like this. Absolutely everything has been translated. The vertex of g becomes the vertex of a. It's been translated by the vector v. And also here g doesn't have any point where it hits the x-axis. Now it's been translated. We can see that the curve now goes down and then it hits the x-axis in 2 different points. So it's kind of this representation that you should be having when thinking about this second method. You are now capable of sketching any types of quadratic functions using the different tools that I've been giving you in this video. So if you like the content, don't forget to like, to share, and to hit the subscribe button. See you next time.